lesson on rate law or rate expression. And you will see that rate law or rate expression is a mathematical expression. It's a mathematical equation. And what it does is it basically quantifies the relationship between concentration of a reactant and the rate of a reaction. So what we have learned is that rate is proportional to the change in concentration of a particular reactant. So let's say in this case, I'm looking at a reaction A goes to B. So rate is proportional to the concentration of A. What that basically means that if I were to increase the concentration of A, my rate will also go up. This is something that we learned based on collision theory. If you guys recall, collision theory states that molecules must collide. They must collide with proper orientation, and they must also collide with sufficient energy. And anything that increases the frequency of those collisions will increase the rate of the reaction, typically. So in this case, if I were to increase the concentration of my reactant, because I'm putting more reactants here, that is going to increase the frequency of collisions between the reactants. And as such, what this is going to do is this is going to increase the rate of my reaction. So what rate law intends to do is to actually dive a little bit deeper into this relationship and figure out exactly how these are related. Maybe somehow if we can quantify the relationship between this. We know based on theory that when I increase this, my rate goes up. Well, here are some of the things that chemists have found out. What chemists have found is for certain reactions, and again, this is different from all reactions, for certain reactions, you can actually increase the concentration of this particular reactant A and nothing happens to the rate. And that is a little bit counterintuitive because it kind of goes against what we learned about collision theory, but that is what we learn when we dive deeper into this. In other cases, what they've noticed is that, let's say, for example, they increase this. Let's use a specific number. Let's say if I double the concentration of this reactant A, what chemists found was the rate actually doubles. And in other cases, what they've found is that when you actually increase the concentration, let's say this time, again, I'll double the concentration of this reactant here, and they've found that actually rate goes up 4 times. Now, this right here is what the rate law or the rate expression is interested in. And in diving deeper and quantifying the relationship between a change in the concentration of a particular reactant and the impact that it has on the rate of the reaction. And typically you will see that, whether doubling, for example, the concentration of A doesn't do anything to the rate, whether doubling doubles it, and whether doubling quadruples the rate, depends on a set of what we call orders of reaction, which are exponents in your rate expression. So let me give you an example of a rate expression. So let's say we have a situation like this where we have A plus B goes to AB, and here my coefficients are these ones here. So if I were to write a generic rate law or rate expression for this, it will look like this. So as you can see here, this is a mathematical equation. This is the rate of the reaction. We already know this. So the units for this would be moles per liter per second. And if you're an IB, that would just be moles per dm cubed per second. That's just molarity per second. So if you guys don't remember, concentration is moles per liter or moles per dm cubed. And because rate, I will record a lesson on kinetics, but since rate is change in the concentration of a reactant over change in time, the change in concentration is going to be moles per liter, and change in time is typically in seconds. That's how you end up with this unit. If you are confused about that, we can always go back and take a look at the kinetics unit. But at this point, let's just focus on this for a second. This guy here is known as the rate constant. Okay, so as the name indicates, this is a constant. However, the value is only constant as long as the temperature remains constant. So temperature must be constant because that is temperature dependent, and no catalyst is added. Now, the reason this happens is because as the value of k increases, as the rate increases, the value of k also increases. So you will see that the larger k value means that you have a faster reaction. So if I'm repeating an experiment twice, 3 times, I'm doing trials, and if I want my rate constant to stay the same for all of my trials, then I will make sure that my temperature remains constant and there's no catalyst added. Both of these factors, if you recall, increase the rate of the reaction, and as such, they will increase the value of K. One of the other things you should know is that K has variable units, and we will talk about that. Basically, what that means is that the units will change. They're not always the same. All right, so the other two important things here, by the way, you notice here that the rate expression is only written for reactants. In this case, I only have 2 reactants. You could have had 1 reactant. You could have had 3, 4, 5 reactants. From this point on, so here I have only 2 reactants. So it's written for 2 reactants, and notice I have 2 exponents. If I had 3 reactants, then I would have 3 exponents. It's Mn and then P, and then from that point on, it is alphabetical. Now, you don't have to use M and N. These are generic words, letters that are used. You could have used X, Y, Z, A, B, C. It doesn't really matter. But to me, I guess one of the most important parts of rate expression or rate law are these exponents, which we call orders of reaction. Okay, so you will notice that every single reaction has its own rate law or rate expression. And really what makes one rate expression different than the next one are these exponents. Now, exponents, these orders, can be fractions. They can be obviously whole numbers. They can be even negative. For us, we are going to focus on 3 exponents, 0, 1, and 2. So you will hear me say 0 order, first order, second order. So for example, if m was equal to 1 and n was equal to 2, I would say that A is first order, or this reaction is first order with respect to reactant A, and second order with respect to B. And while we're talking about this here, the sum of these 2 orders, which is 3, will give you what's called the overall order of reaction. Okay, so let's just take a quick look at what these exponents mean. So let's say we're looking at a simple reaction, A goes to B, where rate here equals K times the concentration of A raised to the power of M. So let's take a look at a scenario where M is equal to 0. So if M is equal to 0, this equation becomes rate equals K times the concentration of A raised to the power of 0. Now, we already know that anything to the power of 0 is 1, and doesn't matter what I do to the concentration of this reactant. You will see that my rate is just going to be equal to K, which essentially means that my rate is going to be constant. The rate's not going to change. Let's just take a quick look at example here. Let's say I start with 1 mole per liter concentration of this A, and my exponent is 0. My K is a constant, so I'm going to leave that aside. My rate will, let's just say it will be 1. If I were to double the concentration of this reactant to 2, again, that's the order here, my rate would still be 1. So just from a math perspective, you will see that this whole term right here, like I said earlier, would just be equal to 1, which means that my rate will stay constant. And it doesn't matter how much of A I put into that reaction, my rate will not change. Now, that's a little bit counterintuitive, like I said earlier, because we know that typically if you increase the concentration of a reactant, your rate should go up. So for a 0 order, so in this case, we will call this 0 order with respect to that particular reactant here. If I were to draw the graph of rate versus concentration, where this is increasing concentration here, by the way, square bracket here means concentration or molar concentration or molarity. So all this time, when I've been talking about concentration, I'm specifically talking about molar concentration. You will see that here, as I increase the concentration, my rate remains the same. So this is the rate versus concentration graph for a 0 order reaction. Now let's take a look at another scenario where we have A goes to B, and in this case, my rate law or my rate expression looks like this. Okay. What will happen here now is my K is obviously constant, but if I were to start with, let's say, 1 mole per liter concentration of this, my rate will be 1, for example. So this would be our standard or a starting point. What I'm going to do now is I'm going to double the concentration of this reactant. So I went from 1 mole per liter to 2 moles per liter, and here I doubled the concentration. And you'll see here that if I were to just simply plug it in here, because of that 1 here, we have basically a situation in math where it's y equals x to the 1. I left the constant out. You will see that my rate will also double. And you will see that obviously if I were to triple the concentration of this, again, 3 to the power of 1, you will see that my rate would also triple. So what we notice here is that your rate actually changes by the same factor as the change in the concentration of your reactant. I double it, the rate doubles. I triple it, the rate triples. We call this directly proportional. So what happens here is we can conclude that rate is directly proportional to the change in the concentration of my reactant. That is what happens when you have an exponent of 1 or when you have a first order reaction. The last situation is where A goes to B, and in here, let's just say M is equal to 2, where rate now equals K times the concentration of A raised to the power of 2. And you can see now that if I were to start with 1 mole per liter of this, let's just say my rate would be 1, K is constant again. If I were to double the concentration of my reactant here, you will see that 2 squared is equal to 4, which means my rate actually goes up 4 times. And if I were to triple the concentration of my original reactant, let's just say, you will see that my rate actually goes up 9 times because it's going up by the square of this. So what we're noticing here is that as I increase the concentration of my reactant, you'll see that my rate actually increases by the square of that. And this is very handy. Now, when we put what we just learned together into a situation like this, where we have rate equals K times the concentration of A times the concentration of B raised to power of 1 and 2, what this now tells me is that if I were to double the concentration of A, my rate would go up 2 times. If I were to double the concentration of B, my rate would go up 4 times. Now, this is very handy if you're a chemist, because if I want to speed this reaction up quickly, I would definitely increase the concentration of B. Why? Because it has an order of 2. And that means that by doubling the concentration of B, I'm actually going to increase my rate 4 times. So understanding all of this, the one question now we can answer is, what does the rate expression, what does this rate law tell us about a particular reaction? If I'm a chemist and I'm looking at this, how is this useful for me? Well, it's very useful because now I know that changing the concentration of B will quadruple the rate. Changing the concentration of A will double the rate. So what does the rate expression show? It basically quantifies the relationship between a change in the concentration of the reactant and how that change impacts the rate of your reaction. Okay. So the next thing we're going to talk about is obviously these exponents and how we come up with these exponents. Well, one of the things obviously you will realize is that exponents can only be determined by experiment. Unless we are looking at the reaction mechanism, and we will deal with that another time. So let's see how we determine the exponents. So the experiment here is actually called the initial rates. It's called the initial rates method. Excuse me. So essentially what we do is, let's say I'm going back to my simple reaction of A plus B goes to AB. What I will do is I will do multiple trials of this experiment. And then I will measure the initial rates. Now, if you don't remember what initial rate is, initial rate, let's say we're looking at a graph of, let's say, volume of hydrogen gas that's being produced in a reaction. This goes back to kinetics. You guys can go back and review kinetics. But you see here, obviously, this is showing me, so this is volume of H2. For example, this is reaction progress. You will see here that obviously the rate of the reaction is fastest at the start, and then the rate of reaction slows down, so the rate is not constant. Initial rate would be the rate right there. So if you were to draw a tangent right at the start of the reaction and measure the rate, we call that the initial rate. So what I will do in these experiments is very quickly, I would repeat this experiment, let's say 3-4 times. By making certain changes, and you'll see what those changes are. And then I would measure the rate for each trial. So let's say, for example, trial 1, I would start with, let's say, a concentration of 1 mole per liter of this, a concentration of 1 mole per liter of this, and then I will calculate the initial rate. Let's say the initial rate here is 2 moles per liter per second. I'm leaving the units out for now. Let's say now I repeat the experiment, so trial 2, I double the concentration of this, and I keep this one constant, and let's say my rate stays the same. And then I repeat it one more time. And this time I keep the concentration of this the same. And I now double the concentration of this. And my rate goes up to 4. So what I have here is a table of results of what we call initial rates. This is the concentration of A. This is the concentration of B. And this is obviously here is my rate. So how can we use this table here, the table of experimental data, to determine what the orders are? So the order with respect to A, I am going to take a look at these trials. So I'll take a look at trial. So let me make this into an actual table here so you guys can actually see the numbers. So if I look at trial 1 and trial 2, you can see here that I doubled the concentration of my A while keeping this one constant, which means B is not affecting my rate. You notice that if I double the concentration of A, my rate did not change. Because of that simple fact, I can now conclude that the order with respect to A is 0. Why? Because the rate did not change. That is what is associated with a 0 order exponent or 0 order reaction. Again, you can see now that when I look at trials 1 and 3, so if I compare trial 1 and trial 3 this time, you can see that this one remained constant, but I doubled the concentration of this. And when I looked at that, you notice that my rate also doubled. So because my rate doubled or changed by exactly the same factor, that is something that is associated with first order reaction. So now my order with respect to B is 1. So just a quick review again. You will do this experiment, which is called the initial rates method. You will do the experiment, measure the initial rate for each of these. You're obviously repeating the experiment. In this case, I'm repeating it 3 times. What I will do, obviously, you notice here is that I am changing the concentrations from trial 1 to trial 2. So trial 1 to trial 2, I doubled this, I kept this one constant. And then trial 3, I kept this one constant, and I doubled this. At the same time, I measured the rate of all of them. And now once I have the data, I analyze the data. So what I concluded was that rate equals K times the concentration of A raised to the power of 0 times the concentration of B raised to the power of 1. That's 0 order, that is first order. Well, we know from math that anything to the power of 0 is 1. So your rate expression or rate law basically looks like this. We're going to remove the A. It's just going to be B to the power of 1. Okay? Now, once you have determined the order and you have written the rate expression, you will then be asked to calculate the value of K. So in order for us to calculate the value of K, we can rearrange that equation for K equals rate divided by change in the concentration of my reactant. In this case, reactant B. You don't need to put the 1 there. I'm just going to put it there. This is basically what the rearranged equation is for K. If I actually want to plug some numbers in here and find the value of K, I'm going to go to my table here. And here, I can use any trial, the numbers for any trial. So I need the concentration of B and I need the rate. The reason I can use any trial is because these trials were all repeated under the same conditions of temperature and there's no catalyst added, which means the K is the same for all of them. So the K is the same for all trials. So if that's the case, I'm going to choose my trial number 1 here. So if I do that, my rate was 2, and then my concentration is just 1. and of course, well, that's raised to the power of 1, and my k value is 2. The last thing you will be asked to find is the units for k. So the units for k, remember earlier we said it was variable. So the units for k is going to follow this equation right there. The unit for rate is mole per liter per second. By the way, L to the negative 1 basically means 1 over L, so 1 over liter. And then concentration is just going to be moles per liter. So you can see here that using math, I can now cancel this moles per liter with this moles per liter. So what I will be ending up with is S to the negative 1 or 1 over S. That's your unit. You will see that the units for K will change depending on your coefficients. So as an example, if my rate law or my rate expression looked like this, in this situation, K is going to be rate divided by concentration of A squared. That's going to be mole per liter or per decimeter cubed if you're an IB, divided by mole per liter times mole per liter. And that basically means that here the moles per liter will cancel with this. What I will end up with is S to the negative 1 over mole times liter to the negative 1. Now, typically, if you're an IB student, this is not how it would be left in a question. You would bring this up. And when you bring this up, it becomes mole to the negative 1 because the exponent here is 1. Liters will become positive. And then S is still to the negative 1. So that would be the unit for this. So again, a quick summary of what we learned is we talked about the rate expression. So you should know that the rate expression now is just a mathematical expression that relates, that quantifies the relationship between a change in the concentration of a reactant and its impact on the rate. In my example here, I'm only showing one reactant. Remember that rate expressions are only written for reactants. Remember that these exponents, which is called the order of the reaction, is determined by experiment. You can determine it from a mechanism, but we're not there yet. But you need to have initial rates data to calculate that, to determine the rates of reaction. And you should know what a zero order or zero exponent means. First order and second order exponents mean as it relates to the rate law, and also be able to calculate the units, the value of K and the units for K.